In this amplifier, the Cascode that we analyzed previously, and in other amplifiers that we have seen and that we will see, we will start from now on to rely on two formula sheets that are posted on the Moodle page. The first formula sheet is a formula sheet for voltage gain for all kinds of transistor amplifier stages. And the second formula sheet is for resistances that we see when looking into terminals of transistors, and also when we combine resistors together. So if you look at the Moodle page of the course, there are two PDF documents there about resistance calculation and gain calculation. So we'll try to use them to analyze, as an example, the Cascode amplifier. We already analyzed it, but we will now try to analyze it using the formula sheets. So let's start with, for example, the gain. Here, as we said previously, we can consider Q1 to be a common source stage and loaded by the input resistance of the next stage. The next stage is a common gate, is Q2. So I can look at the formula sheet for gain. And on the first page of the formula sheet, I will stop sharing the PowerPoint and share the formula sheet now. So you see here on the first page of the formula sheet that this is about small signal voltage gain calculations, and there's a note that no signal, what it says no signal, this means that the node can be a pure DC or a ground node. So I have this number one, this is a common source NMOS and PMOS, and common emitter NPN and PNP. And there are some formulas there. And on the next page, there is common gate, NMOS and PMOS, common base, NPN and PNP. And the third page has common drain, which we haven't seen yet, but we will see shortly. I want the gain of a common source. The first stage in the Cascode is a common source. And I have an NMOS transistor. So this is the circuit that I need. And this is a general common source amplifier where there is an input at the gate and the output from the drain, an RS between source and no signal, which can be a pure DC or ground, and an RD between the output and no signal, which can be a pure DC or ground. So this is the circuit that I need, and I am given that if RS is 0, then the gain is VO over VI equals minus GM RO parallel RD. And this is something that we're familiar with. This is minus GM R prime L, the formula for common source. And also with RS but neglecting RO, I have a formula. And for the MOSFET, if there is an RS and there is an RO, there's also a formula. And with body effect for MOSFET only, there's also a formula with body effect. But in 311, we're now neglecting body effect, so don't worry about that. So in the case of the Cascode, I have a common source amplifier like this one here. and it doesn't have an RS, so RS is 0. So I should use this formula, minus GM RO parallel RD. But what is RD in the case of the Cascode common source, the Q1 stage? RD here represents everything that we will see that appears between the drain of the MOSFET and ground. So this can be just one resistor. This can be a resistor in parallel with a load to ground. So maybe we have an RL between the output and ground, and then the RD in the formula would be this resistor in parallel with RL. Or if this is connected to another MOSFET or another amplifier stage, this would be the input resistance of that amplifier stage. And or a parallel combination of all of the above, like RD and RL, and this is connected from the output here. I'm taking like a wire that is connected to the input of another stage. So this will be a combination of the input of the next stage, RD, in parallel with RL. In the case of the Cascode, I don't have an RD and I don't have an RL, but I have a next stage, which is a common gate. So this RD here that I will use for the common source gain in this formula, minus GMRO parallel RD, this RD would be the input resistance of Q2, the next stage in the Cascode. So where can I get this input resistance formula from? Well, this is the second file, which is the resistance calculation file. So again, there's a formula sheet for resistances, and I will stop sharing the voltage gain formula sheet and share the resistance formula sheet. So this is the resistance formula sheet. Again, it's posted on Moodle, and it has 7 pages. And again, the no signal no's mean pure DC or ground. The first formula is just 2 resistors. So considering the resistance looking into this terminal with R1 and R2 from this node to ground to no signal, the resistance R would be R1 parallel R2. Another case is this, where the resistance seen is R1 plus R2. Again, the resistance seen means that I'm connecting a test source here, Vx, across these 2 terminals, Vx, and I'm finding Ix, and the resistance seen is Vx over Ix. If I'm looking into one terminal only, like the first case here, case 1, it means that I'm finding the resistance between this and ground, the terminal and ground. And the third formula is the Rxy, Rx plus Ry plus GM Rx Ry. And then a list of formulas for NMOS and PMOS. This is when I'm looking into the gate and I always see an infinite resistance. And this is when I'm looking into the drain and with no signal at the source. And these are rules that we have seen, and I see a small RO. And this is when I'm looking into the drain with an RS between source and ground. And in this case, I see RO plus RS plus GM RO RS. So these are familiar. Already we know about these rules. And this is something that is an application of number 6. If I have 2 MOSFETs and no signal at their gates, the resistance seen looking into the drain of M1 would be RO1 plus RO2 plus GM1 RO1 RO2. So all the rules that we have seen so far are summarized in this document. This is the common gate. So here's a MOSFET with no signal at the gate and a small RD between drain and no signal. And if lambda is 0, if I neglect lambda, that is Rho is very, very large, I get 1 over Gm, and I get this formula if Rho is not very large, lambda is not 0. So this is what we derived in the case of common gate. And then we have some other formulas for the BJT, input resistance at the base and at the collector and at the emitter. So what do I need now for the cascode? I go back to this. Q2 is like M here in this circuit. So I'll use the formula to find the input resistance for the stage, for the common gate stage in the cascode consisting of Q2. So the input resistance, I have a formula here, is 1 over Gm if lambda is 0, or Rd plus Ro over 1 plus Gm Ro. So this is the more general formula, Rd plus Ro over 1 plus Gm Ro. And we're not told that lambda is 0, so I'll have to use it. What is Rd for Q2 in the cascode? Q2 in the cascode had a current source between its drain and the supply. And this current source we assumed was ideal. So the small signal output resistance of a current source when it's ideal would be infinite. So this small Rd, in the case of Q2 in the cascode, would be infinite. And if you calculate R with an infinite Rd, so infinity plus Ro over 1 plus Gm Ro would be infinite. And therefore, the input resistance for Q2 in the cascode would be infinite. Again, by applying this formula. If Rd is not infinite, if the current source is non-ideal, has a certain output resistance, then this is how I can find the input resistance of Q2 looking into its source terminal. So to conclude, these are two sets of formulas that will help us a lot in our calculations. And we will almost use them exclusively without doing any detailed circuit analysis. So from now on, we will just refer to the formula sheet. I want the gain of a certain stage. I want the resistance seen looking into a certain terminal. I just look up the formula from the formula sheets and use it. So let's go back to our cascode. And this is the situation. We said that this is a common source. And we have the formula from the formula sheet, minus GM1. The gain is minus GM1, RO1 parallel. We had like an RD in the formula there. And RD is whatever is between the drain of Q2 and ground. So RD was connected in the formula sheet like this. That was RT in the formula sheet. So this is my Q1 now. And its RD is the resistance seen looking into the source terminal of Q2. And there is a formula for this from the formula sheet. If I'm looking into the source of a MOSFET with no signal here and an RD here to a no signal node here, I'm looking into the source terminal of this MOSFET. And there is a formula for that. Again, from the formula sheet, it's RO2 plus RD over 1 plus GM2 RO2. So what is RD for Q2 here? Well, this is ideal. And in the small signal analysis, this becomes an open circuit. So RD goes to infinity. So this is an infinite RD in small signal analysis. But even if it's not an ideal current source and has a certain output resistance, let's call it ROX. So let's say non-ideal output resistance ROX. Then this is what I will use here as RD. So if this is non-ideal and has an output resistance ROX, this becomes the RD for Q2 and the formula. And I will use it here. So this is ROX. Let's say that there is an RL. What happens? Well, that's easy because RL and ROX would be in parallel. RL is from the output to signal ground, real ground, and ROX is from the output to signal ground. So what should I use now? ROX parallel RL, that's it. So ROX parallel RL would be this RD in this formula. And you see how this simplifies the analysis. I'll just, as long as I understand the meaning of like the resistance looking into a terminal, or I can identify the type of the stage, or just know how to apply the formula sheet equations, then I don't need to do any detailed small signal circuit analysis. I'll just use the formulas. So for the output resistance, we did an analysis for that. But if I is ideal and I want the output resistance looking into the drain of Q2, when I'm doing output resistance calculation, VI is 0, so no signal at the input. So no signal here, no signal here because it's a pure DC. I'm looking into the drain of Q2, and there are two MOSFETs in series like this. Again, I look up the equation in the formula sheet, and there is a circuit just like this one that tells me that this is RO1 plus RO2 plus GM2, RO1, RO2. So that's it. I don't need to do any detailed analysis, really. Just look up the formula and the formula sheet. The voltage gain, we already discussed that, and we can just use the formulas. Of course, you need to consider the loading effect. So whenever you have two stages, there is loading effect. The stage number I plus 1 would load stage I, and the input resistance of stage I plus 1 becomes the load resistance of stage I. Other than that, you just apply the voltage gain formulas from the formula sheet, and it should work. In the case of the high frequency response, also, we did a lot of OCTC resistance calculations. So for example, here, we said that the resistance seen by CGS1 is R sig. And the formula sheet tells me there is a formula that says, if you're looking into a terminal like this and you have an R1 and an R2, to no sig, then you see R1 parallel R2. You see here R1 parallel R2. All right, so this is the situation here. CGS1 is replaced by a test source, and I want to find the resistance seen looking into this terminal. And I have an R1 like this and an R2 like this. So to apply the formula of the formula sheet, I need to find R1 and R2. Looking left, there is only R sig, so R1 is R sig. Looking right, I see the gate of a MOSFET. So that's infinite resistance, no current will flow. So R1 parallel R2 will therefore be R sig. which is what we calculated previously. But now we did it with the help of the formula sheet. Again, same thing here. I want to find the resistance seen by the capacitance at the output node. So here, what is the resistance seen here? So again, let's call this R1 and this R2. The resistance R would be R1 parallel R2. And then we do now an analysis of what is R1 and what is R2. So R1 is the resistance seen looking into the drain of a Q1 with no signal at the gate. And there's a formula for that in the formula sheet. It's RO1. You can look up the formula sheet, and if you're looking into the drain of a MOSFET with no signal at source and no signal at gate, it's small RO1. And also from the formula sheet, you can look up this small R2 is the resistance seen looking into the source terminal of Q2. And there is a formula for that. It is RO2 plus small rd over 1 plus GM2 RO2. This is the formula from the formula sheet. It uses a small rd again. But what is small rd? It's the resistance between the drain of Q2 and ground. So what do I have between the drain of Q2 and ground? I have RL. So here in this formula, I will use RL. And the resistance seen by the capacitance, which is R1 parallel R2, would be RO1 parallel with all of this here. And again, this is the same formula we arrived at. Same thing for this one. So this is R1, and there is an R2 to ground, but it's rotated in this case. So R2 is like this, and that's fine. I still see R1 parallel R2 when I want to calculate R. And if I look at the formula sheet and I'm looking into the drain of a MOSFET with no signal here and no signal here, and there is another MOSFET between the source of the first and ground, then R2 will be from the formula sheet RO1 plus RO2 plus GM2 RO1 RO2. R1 is simply RL, and R is R1 parallel R2. So you plug in RL parallel with this quantity. This one, because CGD1 is not connected between a node and ground, I have to do the analysis twice. So I have to see the resistance here, looking at this terminal, and we already did this when we did CGS1. So to do this parallel with this, and therefore just R sig because there's no input resistance at the gate of Q1. And then the resistance here, looking like this, would be this, parallel with this. And we already calculated that when we did the output capacitance. So we have an answer for that. We know what is the value here. But for CGD1, what is the resistance seen by CGD1? Looking at the formula sheet, this is an RXY. And it will be R sig plus this R whatever star plus GM1 R sig R star. So all of this analysis can be done using formulas from the formula sheet. Okay, one result that we got from the Cascode is the output resistance. The output resistance of the amplifier was RO1 plus RO2 plus GM2 RO2 RO1. And this is interesting because if I have a single MOSFET, the output resistance is just RO1. If I have a cascode, so two MOSFETs, what am I getting? Am I getting like RO1 plus RO2 or what? Actually, I'm getting a much larger resistance than RO1. I'm getting GM2 RO2 times RO1, and GM2 RO2, the product GM-RO for a MOSFET or for a BJT, this is a large number. So say this is 40. So if I have one MOSFET, I get an output resistance, which is small RO. If I have two MOSFETs, what do I get? I get 40 times RO. So that's a much larger output resistance. So this is the result. This is the effect of cascoding. And maybe we can benefit from this somewhere. If you remember when we started this course, we started with a discussion of current sources, and we said that the output resistance of a current source gives me how much the current would vary when the voltage varies. So if the voltage increases, the current changes, the output resistance is like a measure of how much the current will change. And it gives an indication, the smaller the output resistance, the more the current will change and the less ideal the current source is. So when we get something like this, we have a circuit that can give me a large output resistance by just cascoding MOSFETs or transistors. Maybe this can help in the current sources. So if I have a current source that has a small output resistance, it means that the output current changes a lot when the voltage changes, and it's not really close to ideal. How can I improve on that situation? I should increase its output resistance. And now we have a way to do that. So instead of using just one MOSFET, add another MOSFET and do this cascode combination. And this way you will get a much higher output resistance. And remember the equation for delta IO, which should be ideally zero. Ideally, is delta VO, the change in output voltage divided by the output resistance. So ideally, delta IO should be zero and RO should be infinite. If I'm getting a small RO, that's bad for a current source. And delta IO would be large. So how can I make RO bigger or much bigger? Now we have the cascoding, which can make the output resistance bigger. So instead of using just one MOSFET, take the output not from here, add this other MOSFET and take the output from here. And now the output resistance is much higher. So almost GM-RO times bigger. So this is like a side note that cascoding increases output resistance, and therefore, if I am facing an issue with a small output resistance and I need to make it bigger, I need a larger output resistance in a circuit, then cascoding may help. Here's the BJT version of the Cascode, and it's pretty similar to the MOSFET version. I have two NPN transistors, Q1 and Q2. The input is at the base of Q1. The emitter of Q1 is grounded. The collector of Q1 is connected to the emitter of Q2. The base of Q2 is at DC, and the collector of Q2 is the output. So again, we can analyze this by noticing that this is a common emitter. Q1 is a common emitter, and there is an intermediate output here between Q1 and Q2. So common emitter with the input resistance of Q2 as a load. And Q2 is a common base. And the output is taken from the collector of Q2 while the input is at the emitter. The base is at DC, so no signal here. So that's a CECB combination. And we can analyze it like this if I want to find the voltage gain or the input resistance or the output resistance. So the open circuit voltage gain, for example, is let's analyze it as a common emitter. This is common emitter, and from the formula sheet we get that the gain of common emitter is minus GM1 RO1 in parallel with whatever appears between collector and ground. So whatever RC, let's call it RC. So RC is whatever appears between the collector of Q1 and ground. In this case, what do I have between the collector of Q1 and ground? I have just the input resistance of Q2. So this here is the resistance seen looking into the emitter of Q2. So I go to the formula sheet, and the formula for that is, if I'm looking into the emitter of a BJT, then I'm writing here the formula from the formula sheet. What you will see is R pi in parallel with small rc plus RO, in this case RO2, divided by 1 plus GM2 RO2. So this is from the formula sheet. If you're looking here, so this is RC. If you're looking into the emitter of Q2, you will get this formula from the formula sheet. What is small rc? Small rc is whatever is between the collector of Q2 and ground. What do I have in this case? I have this current source. And if it's ideal, then small rc would go to infinity. If it's not ideal, small rc would be RO of I source. So we plug this value here. In case the current source is ideal, this will go to infinity and RC will be just R pi. If I is ideal. So this is RC, R pi. If the current source is not ideal, RC would not be infinite, and I will get whatever quantity here in parallel with R pi. So I'll get the resistance which is smaller than R pi. So back to the load on the common emitter Q1. If we continue with the assumption that I is ideal, the gain of Q1 will be minus GM1 RO1 parallel R pi 2. So this is the gain of Q1. What about the gain of Q2? Q2 is a common base, and I have a formula for common base. So I go to the voltage gain formula sheet and look for common base. And I see there that the common base has a gain of, this is again from the formula sheet, GM plus 1 over RO into RD parallel RO. RD is what we call here small rc, so same thing. So same as small rc. So that's the resistance that appears between the collector of Q2 and ground. If I is ideal, this will be infinite. And the gain would be Gm plus 1 over Ro times just Ro. So 1 plus Gm Ro. And Gm2 Ro2 because I'm talking about Q2. So that's it. This is what we will get for open circuit voltage gain. For the first stage, minus Gm1 Ro1 parallel R pi 2. For the second stage, 1 plus Gm2 Ro2. And the overall would be the product. The input resistance by inspection is simply R pi 1. If you go back to the circuit, the input resistance here by inspection, R pi 1. And of course, if you check the formula sheet, you're looking into the base of a BJT with emitter grounded. The resistance seen looking into the base would be R pi. So input resistance by inspection or by formula sheet, R pi 1. Output resistance, let's see, the output resistance is here. So it will be this in parallel with this. If I is ideal, this will be an infinite resistance. So we'll get just this R looking into C2. Looking into C2, I'm looking into the collector of a BJT with no signal at the base and some resistance between emitter and ground. What is the resistance between the emitter of Q2 and ground? So I'm looking into the collector of Q2 with no signal here and a resistance between E2 and ground. This resistance between the emitter of Q2 and ground is the resistance seen looking into the collector of Q1 and ground. And when I'm doing output resistance calculation, there's no signal at the input. So the base of Q1 would be no signal, the emitter of Q1 would be no signal, and I have a formula for that. That's Ro1. If you look at the formula sheet, you're looking into the collector of a BJT with no signal at base, no signal at emitter, you will see a small Ro1. So back to the output resistance, if I'm looking now into the collector of Q2 and with a resistor Ro2, again, looking at the formula sheet for resistance calculations, looking into the collector, what you will see is from the formula sheet, Ro1 plus Ro2 parallel R pi 1. There, actually in the formula sheet there, Q1 is above Q2. So Ro2 plus Ro1 parallel R pi 2 plus Gm2 Ro1 parallel R pi 2 Ro2. So we have a formula for this, and that's the formula. This is what we get. This is the output resistance of the BJT Cascode. And if in case R pi is much less than Ro, which is usually the case, we get an output resistance which is beta times Ro. Again, nice result if I'm looking to increase the output resistance, or I'm looking to find a circuit that gives me a large output resistance. This circuit gives me beta times Ro. If I have one BJT, the output resistance is small Ro. If I have a cascode of 2 transistors, the output resistance becomes beta times bigger. And beta is a large number, so this is a large increase in the output resistance value.